Hello everyone, I am Dr. Chalapathi Rao, Associate Professor, Department of ECE at VJEC, Hyderabad. Today we will discuss about the low-pass RC circuit for sinusoidal and step input responses in linear wave shaping circuits. Now what is the linear wave shaping? The definition of the linear wave shaping is the process whereby the form of a non-sinusoidal signal is altered by transmission through a linear network is called the linear wave shaping. A linear network is the network made up of linear elements only. Here resistors, capacitors, inductors are called the linear elements because the current passing through the elements is proportional to the applied voltage. There is a linear relation between the voltage and current. So here the linear wave shaping is the process of modification of signal shape using linear RC circuits based on the time constant and input signal type. When a sinusoidal signal is applied to the linear network, the output is same as the sinusoidal in nature. There is no change in the output waveform shape, but amplitude and phase will be changed. Second, when the non-sinusoidal signal such as step, ramp, pulse, square wave is applied to the linear network, the output waveform shape will be changed. Here there are two types of linear wave shaping circuits are there. One is the low pass RC circuit and second one is the high pass RC circuit. Now coming to the low pass RC circuit, a circuit the low pass circuit transmit only low frequency signal and attenuates or stop the high frequency signal. Here this is the circuit. Here there are two components are there. One is resistor and another one capacitor. The resistor is connected in series and the capacitor is connected to the ground. The output voltage is across the capacitor. So here the capacitor is frequency dependent in terms of its reactance. The capacitive reactance is denoted by Xc, that is equal to 1 by omega C, where omega is equal to 2 pi f. So 1 by 2 pi f C. So here there are three cases we need to discuss. The first case one is at zero frequency the reactance of the capacitor is infinity. That is, the capacitor acts as an open circuit. So the entire input voltage appears at the output since the output is the same as the input and also the gain is unity. So here if f is equal to 0, the reactance of the capacitor Xc is equal to 1 by 0 into 2 pi C, so that is equal to 0, 1 by 0 that is equal to infinity. The reactance of the capacitor infinity, the circuit is open, so the entire input voltage appears at the output. Therefore V0 is equal to Vin and gain A is equal to V0 by Vin, that is equal to 1. So this is the first case. Coming to the second case, case 2, as frequency increases, the reactance of the capacitor is decreases and the output voltage also decreases and gain also decreases. Here, so F is increases, the reactance of the capacitor Xc is decreases and output voltage is also going to decrease and gain also decreasing. So here, so up to cutoff frequency, here the input is output is equal to input. So here Fc is the cutoff frequency. The cutoff frequency is defined as the frequency at which gain is 1 by root 2 of its maximum value. So here, so at Fc the gain is 1 by root 2 of its maximum value. Here the maximum value is 1. So 1 by root 2, that is 0.70 value. The gain A is equal to 1 by root 2 of its maximum value. So that is equal to 0.707. So after cutoff frequency, that means in the case 3, if the frequency is very high, that is infinity, so the reactance of the capacitor here is short circuit. So because the reactance of the capacitor is So f equal to very high, let us consider infinity. So xc is equal to 1 by infinity. 1 by infinity equal to 0. If the reactance of the capacitor is 0, the capacitor circuit is going to short. So if the circuit is short, the output is connected to the ground. So V0 is equal to 0 and gain also 0. V0 is equal to 0 and gain A is equal to 0. So here for high frequency signal, the gain is decreasing towards to 0. For low frequency signal, both output is equal to input, so that is equal to constant. So this up to cutoff frequency is known as the pass band. After cutoff frequency, here the amplitude and gain is going to reduce towards to 0. This part is the stop band. And here, so only here we'll get the upper cutoff frequency, that is upper cutoff frequency is denoted by F2. So here the lower cutoff frequency is F1. So F1 is itself 0. So now the bandwidth is equal to the difference between upper cutoff frequency and lower cutoff frequency, F2 minus F1. So here F1 is equal to 0. So bandwidth is equal to F2 only, cutoff frequency only. Now I'm going to explain sinusoidal input response. Now if the input voltage is sinusoidal, now VI of t expressed as VI of t equal to Vm sin omega t, this input voltage applied to the low pass RC circuit. Now apply the KVL to the circuit. Here the equation VI of t applied voltage is equal to voltage across R into I of t plus voltage across C 1 by C integral of I of t dt. So this is the equation number 1. Now taking Laplace transform on both sides, and initial condition to be 0. So Vi of t Laplace transform is Vi of s, that equal to R is a constant and I of t is Laplace transform is I of s plus 1 by C integral Laplace transform 1 by C s I of s. From this equation I of s is common here. Now R plus 1 by Cs. So that is equal to I of s into here the denominator is Cs. So RCS plus 1. Now I of s is equal to Vi of s by 1 plus RCS into, here we'll get the numerator CS. Now this is equation number 2. And coming to the output, so the output is across the capacitor. Now V0 of t is equal to voltage across the capacitor. The equation is 1 by C integral of I of t dt. So let us consider this is equation number 3. Again taking Laplace transform on both sides. Taking Laplace transform on both sides. So V0 of t Laplace transform is V0 of s equal to 1 by C integral Laplace transform 1 by C s into I of s. So this is the equation number 4. Now substituting equation 2 in equation 4, we get the output voltage V0 of s is equal to 1 by Cs into, where I of s is equal to Vi of s into Cs by 1 plus RCS. Here CS cancelled and V0 of s is equal to Vi of s by 1 plus RCS. Now the output and input by input is equal to V0 of s by input Vi of s is equal to 1 by 1 plus RCS. So this is called transfer function. The transfer function is defined as the ratio of Laplace transform of output to the Laplace transform of input. Here V0 of s by Vi of s is equal to H of s. So that is equal to 1 by 1 plus RCS, or you can write 1 by 1 plus S RC. So this is the S domain function. So let us consider here, this is the equation number 5. Equation number 5. Now coming to in frequency domain, S replaced by j omega. Here H of j omega is equal to 1 by 1 plus j omega RC. So that is equal to 1 by 1 plus j, where omega is equal to 2 pi f RC, that is equal to gain A. Next, here we need to derive the frequency responses. Here there are two frequency responses. One is the magnitude response and second one is the phase response. Now first, magnitude response. Magnitude response mod A is equal to 1 by square root of real part square plus imaginary part square. Here from the equation 5, so real part is 1 and imaginary part j into 2 pi f RC. So here imaginary part is 2 pi f RC whole square. And the phase response is theta, that is equal to, here the numerator is 1, so the phase is 0, denominator 1 plus j 2 pi f RC. So the phase is minus tan inverse of imaginary part 2 pi f RC by 1. So here this is the equation number 6 and this is equation number 7. So again, magnitude response is equation number 6 and phase response is the equation number 7. Now at the upper cutoff frequency, F2 gain is 1 by root 2 of its maximum value. Now, so this function is here mod A is equal to 1 by root 2 is replaced by in equation number 6. Now from equation number 6, mod A replaced by 1 by root 2, that is equal to 1 by square root of 1 plus 2 pi f RC whole square. Now squaring on both sides and cross multiplication. So finally we get 1 plus 2 pi f RC. So here at f equal to f2. So f replaced by f2. So f2 1 plus 2 pi f2 RC square is equal to 2. Now 2 pi f2 RC whole square is equal to, here 2 minus 1 will get 1 and square root on both sides will get 2 pi f2 RC is equal to 1. F2 is equal to 1 by 2 pi RC. So this is the upper cutoff frequency in the low pass RC circuit. So here now, so this F2 is applying substituting in both equation number 6 and equation number 7. So here, so equation number 6, mod A is equal to 1 by square root of 1 plus 2 pi f RC, where 2 pi RC, here F2 equal to 1 by 2 pi RC. Now 2 pi RC is equal to 1 by F2. Now substituting this 2 pi RC in equation number 6, so mod A is equal to 1 by square root of 1 plus f by f2 whole square. So this is equation number 8. And phase theta is equal to minus tan inverse of 2 pi RC, that is equal to 1 by f2. So f by f2. So this is the phase response. Coming to the graph, the frequency versus gain. So here at 0 frequency, so 1 plus f by f2, if f equal to 0, so 0 by f2, 0 square, 0 plus 1, so square root of 1, 1 by square root of 1 will get the 1. At 0 frequency, that is at low frequencies, gain is equal to unity. Now second, at f equal to f2, so f2 by f2 here, so f2 by f2 is equal to 1 square, so plus 1, 2 square root of 2, so 1 by root 2, that is equal to 0.70. At upper cutoff frequency, the gain is 1 by root 2. And if f is increasing towards to infinity, very high frequencies, that is if f equal to infinity, infinity by f2, that is infinity, infinity square plus 1, infinity, square root of infinity also infinity. So 1 by infinity is equal to 0. So gain is the 0. Now here up to upper cutoff frequency is the pass band, and after upper cutoff frequency is the stop band. So this is the sinusoidal response of the low pass RC circuit. Next, step input response of the low pass RC circuit. Consider the step input voltage of magnitude V is applied to the low pass RC circuit having a time constant RC. A step voltage VA of t can be mathematically written as VA of t is equal to V volts for t greater than or equal to 0, 0 for t less than 0. So this is the graphical representation of input signal. So here for t greater than or equal to 0, the input voltage is constant, that is V volts. So this input signal is applied to the low pass RC circuit here. Now taking Laplace transform of the input signal. So here VA of t Laplace transform is VI of S equal to Laplace transform of V, that is equal to 1 V by S. Let us consider this is equation number. So previous we have equation number, this is 9, and now this is equation number 10. Let V dash is the initial voltage across the capacitor. So the initial current across the R is applied voltage is V volts and initial voltage across the capacitor V dash. So initial current across the resistor is V minus V dash by R. Okay. Now writing KVL around the loop. So here VI of t is equal to voltage across R plus voltage across C. So voltage across R is R into I of t plus voltage across C is 1 by C integral of I of t dt. This is equation number 11. Now differentiating with respect to t. So VI of t derivative differentiating with respect to t. So d by dt of VI of t is equal to R into d by dt of I of t plus 1 by C integral derivative cancel, you'll get I of t only. So this is equation number 12. Since VI equal to VI of t input voltage is V volts constant. Now derivative of input voltage, derivative of constant is equal to 0. Therefore, from this 12th equation, d by dt of VI of t is equal to 0. So 0 is equal to R into d by dt of VI of t plus and 1 by C into I of t. So this is equation number 13. Now taking Laplace transform on both sides. So 0 Laplace transform is 0 and R into derivative of current Laplace transform is R into S into I of S minus initial current. So initial current is denoted by I of 0 plus and plus 1 by C, that Laplace transform of I of t is I of S. Now here R into minus I of t is equal to R into I of 0 plus is equal to R into S into I of S plus 1 by C into I of S. Here R into I of S is common. So S plus 1 by RC. So that is equal to R into I of 0 plus. So here both sides R are cancel. Now I of 0 plus is equal to I of S into S plus 1 by RC. So I of S is equal to, here I of S is equal to, so I of 0 plus by S plus 1 by RC. This is equation number 14. The initial current I of 0 plus is given by I of 0 plus is equal to V minus V dash by R. So this is equation number 15. Now substituting equation 15 in equation 14, we get I of S is equal to, where I of 0 plus is V minus V dash by R into S plus 1 by RC. So this is equation number 16. Coming to the output, so from equation number 1, so here equation number 1 from equation number 1, so here input voltage Vi of t is equal to R into I of t plus 1 by C integral of I of t. Here the voltage across the capacitor is called the output voltage. It is V naught of t. So from this equation, V naught of t is equal to Vi of t minus R into I of t. Now taking Laplace transform, this is the equation number 17. Now taking Laplace transform on both sides, V naught of t Laplace transform is V naught of s is equal to Vi of t Laplace transform is Vi of s minus R into I of s. So this is equation number 18. From here input Vi of s is equal to input is step voltage. The Laplace transform of step input voltage is V by s. So and R into I of s, where I of s is equal to V minus V dash by R into s plus 1 by RC. Okay, the output voltage V naught of s is equal to Vi of s minus R into I of s, where Vi of s is equal to V by s minus R into I of s is equal to V minus V dash by R into s plus 1 by RC. So here RR cancel. Now V naught of s is equal to V by s minus V minus V dash by s plus 1 by RC. So this is the V naught of s, the output equation in s domain. So let us consider this is equation number 19. Now taking inverse Laplace transform on both sides. So V naught of s inverse Laplace transform is V naught of t. V by s inverse Laplace transform is V minus V minus V dash is the constant, and 1 by s plus 1 by RC inverse Laplace transform is e power minus t by RC. So this is the V naught of t. So the time domain equation from s domain. So let us consider this is the equation number 20. Here where V is equal to V final value and V dash is the V initial value. Therefore, V naught of t is equal to V final minus V initial into e power minus t by RC. If the initial voltage V initial is equal to 0, that means the capacitor is initially uncharged. That means initially uncharged, that means V initial value is 0. Therefore, V naught of t is equal to V final minus 0. So that is V final into e power minus t by RC. So here the V final is common. Now V naught of t is equal to V final of 1 minus e power minus t by RC. So here the V final minus V initial into e power minus t by RC is the equation number 21. And V naught is equal to here the initial value initially uncharged. So that means initial value is 0. Therefore V naught of t equal to V final minus V final into e power minus t by RC. So here V final is common. So 1 minus e power minus t by RC. Here where V final is equal to maximum voltage, that is the V volts. So therefore V naught of t is equal to V into 1 minus e power minus t by RC. So this is the final equation for the low pass RC circuit for step input. So this is the graphical representation. The x-axis is time and y-axis is the output voltage V naught. The output is exponentially increasing towards to the maximum value V volts. Coming to the expression for the rise time. So the definition of the rise time is the time taken by the output voltage to rise from 10% to 90% of its final value. It gives an indication of how fast the circuit can respond to a discontinuity in voltage. Assuming the capacitor is initially uncharged, So therefore, the output voltage V naught of t is equal to V into 1 minus e power minus t by RC. Now here the time required for the output to achieve 10% of its final value can be obtained. So at t equal to here, at t is equal to T1, output voltage V naught of t is equal to 10% of V volts. So 10% of V volts is 0.1 volts. Therefore, so V naught of t is equal to 0.1 volts. So 0.1 volts is equal to V into 1 minus e power minus t replaced by T1 by RC. So here V cancel. So 0.1 is equal to 1 minus e power minus T1 by RC. So e power minus T1 by RC is equal to 1 minus 0.1. So that is equal to 0.9. From this equation, T1 minus T1 by RC is equal to natural logarithm of 0.9. Now T1 is equal to RC into, so here minus T1 by RC is equal to natural logarithm of 0.9. Now T1 is equal to minus RC into natural logarithm of 0.9. So minus natural logarithm of 0.9, you can write it as natural logarithm of 1 by 0.9. So natural logarithm of 1 by 0.9 is, the value is 0.1. So this is 0.1 RC. So this is the time T1. Now similarly, the time required for the output voltage to achieve 90% of its final value. So at t equal to T2, V naught of t is equal to 90% of its final value. So the final value is V volts. So that is equal to 90% of V volts is 0.9 volts. Therefore, the output voltage 0.9 volts is equal to V into 1 minus e power minus T2 by RC. So here also V cancel. 0.9 is equal to 1 minus e power minus T2 by RC. So e power minus T2 by RC is equal to 1 minus 0.9. So that equal to 0.1. So minus T2 by RC is equal to natural logarithm of 0.1. T2 is equal to RC into minus natural logarithm of 0.1 can be written as natural logarithm of 1 by 0.1. So natural logarithm of 1 by 0.1 is equal to 2.3. So 2.3 into RC. This is the T2. Now the rise time TR is equal to the difference between T2 and T1. So here TR is equal to T2 minus T1, that is equal to T2 equal to 2.3 into RC minus T1 is equal to 0.1 RC. So 2.3 minus 0.1, so that equal to 2.2 into RC. So this is the rise time TR. So here the rise time is proportional to the time constant RC. Now the relationship between upper 3 dB frequency and rise time. Here upper 3 dB frequency or upper cutoff frequency. So cutoff frequency is also called as 3 dB frequency. So here the upper cutoff frequency is F2 and lower cutoff frequency is 0. So the bandwidth is equal to F2 minus F1. So F1 is 0. So bandwidth is equal to upper 3 dB frequency or upper cutoff frequency. So here the upper cutoff frequency F2, that is equal to bandwidth is equal to 1 by 2 pi RC. And the rise time TR is equal to 2.2 into RC. From upper cutoff frequency F2 is equal to 1 by 2 pi RC. Now RC is equal to 1 by 2 pi F2 or 1 by 2 pi into bandwidth. Okay, now substituting the time constant RC in rise time function. So here the rise time function 2.2 into RC. So 2.2 into where RC is equal to 1 by 2 pi into F2. So 2.2 by 2 pi where pi is equal to 3.14. So 2.2 by 2 into 3.14, that is equal to 0.35 by F2 or 0.35 by bandwidth. So this is the rise time relationship between rise time and bandwidth, or rise time and upper cutoff frequency. So rise time is inversely proportional to the bandwidth, or the rise time is inversely proportional to the upper cutoff frequency or upper 3 dB frequency. Now coming to the time constant RC. So the definition of the time constant RC is the time taken by the output to rise to 63.2% of amplitude of the step input. It is same as the time taken by the output to rise to 100% of the amplitude of the input step if the initial slope or rise is maintained. So coming to this graph, so here the maximum output is exponentially increasing towards the maximum value. Here the maximum value is the V volts. This is the step input volt, V volts. Now, so the output is the time taken by the output is rises 63.2% here. So at that time, this is tau. So 63.2% means 0.632 volts. So at the rise time time constant tau is equal to here RC. So this is the step response of the low pass RC circuit with various relations between rise time and bandwidth and time constant and what is the cutoff frequency. So these are the discussed in this concept. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.